Just like in Calculus 1, sometimes a tangent line can be used to approximate a function near a given point. There's a similar concept in vector value functions. Okay, since a velocity vector at time t points in the direction of motion, so it would show how the curve is instantaneously pointing at that time, it must be tangent to the curve c traced by the vector value function at the time t, and hence the definition. If c is a smooth curve, and that's important, if it's not smooth we wouldn't know if this was true, but let it be a smooth curve traced by a vector value function r of t on an open interval I, that's a t interval, then what's called the unit tangent vector t of t at time t is defined as, think about it, unit means its length is 1, tangent means it points in the direction of motion at the time, and so therefore the vector r prime would do that, and the fact that it's a unit vector means it's going to have length 1. And so we just find our vector r prime of t and then divide it by the length of r prime of t, wherever r prime of t is not 0, because you can't divide by length of a vector if it's 0, but that would turn it into a unit tangent vector. Okay, here's an example of one. So let's find the unit tangent vector for the curve traced by the vector value function r of t at the given point where t equals pi over 2. And sketch the graph and the unit tangent vector, and that's not something I would expect you to do by hand, but this one you might be able to, but it's not something I'm going to expect. So if this is our vector r of t, 2 cosine ti plus 3 sine tj plus tk, you might recognize that as a helix. We've seen something like that before. R prime of t would be negative 2 sine t plus 3 cosine t, negative 2 sine ti plus 3 cosine tj plus derivative of t is 1, of course, so 1 times k. So when we want to find its length, to find the length of this vector, we take the square root of the I component squared plus, that's this, plus the j component squared plus the k component, where is it? There it is, squared. And so that would be 4 sine squared t plus 9 cosine squared t plus 1. That's the square root of all that. Now, a good question would be, what is our unit tangent vector function? And here's our unit tangent vector function. Negative 2 sine t, well, that's essentially the vector r prime of t is in the numerator. I just did cut and paste really to create this. And over this denominator, which represents the length. And so then it gets interesting and says, yeah, but find the unit tangent vector. See, this is the function that generates unit tangent vectors for every value of t, but this says find the one where the value of t equals pi over 2. So we put in pi over 2, then sine of pi over 2 of course is 1, so we got 1 times negative 2i. Cosine of pi over 2 is 0, so the j component goes to 0 and the k is still 1. What goes on in the denominator is that since the cosine of pi over 2 is 0, then this whole part is 0, and we got 4 times the sine of pi over 2 squared, which is 1 squared, so we got square root of 4 times 1 plus 1, so square root of 5. And so this is our unit tangent vector. Now here's the helix itself. I suppose you can kind of see that helix. It's, you know, like spinning around, so to speak, a little bit fatter in one direction than it is in the other. And the question is, when t equals pi over 2, that means z would be pi over 2. That's about pi over 2, about 1.57. So if you can figure out from looking across the z-axis, if that's 5, 1.57 would be about here. So somewhere around in here, maybe we're going to find a unit tangent vector for this and draw it on that graph. And when I draw it, I can't rotate it anymore, but that would be the unit tangent vector right there. And so let's, well, stop right there.